and gentlemen, please put your hands together and welcome Sapphire Wanmer to the stage.
Okay, thank you. Right, so imagine I've met you at the bar and we get chatting and I tell you that I'm a volcanologist. What's that? And what does that make you think? So I usually get two comments. I usually get comments about Star Trek and the Vulcans, and otherwise people are like, but there are no volcanoes in the UK. Little do they know that there are actually loads of volcanoes in the UK. Okay, so they're not erupting, they're not active, but they were once, a long, long time ago. Several millions of years ago, in fact. For example, 60 million years ago, there was great outpourings of lava all across Northern Ireland and parts of Scotland. So that is what we see today as the Giant's Causeway. So this occurred at a time, 60 million years ago, when the North Atlantic Ocean was beginning to open. And this was because of the pulling apart of the Earth's crust. And around 55 million years ago, this pulling apart caused the formation of new oceanic crust. So this is the hard outer shell of the planet that lies beneath the oceans. So while this crust was forming, we had huge volcanic eruptions that pumped vast amounts of ash into the atmosphere, which got transported all the way across northwest Europe. So remember that the eruption at that unnameable Icelandic volcano 5 years ago. It swept ash all the way across the UK and closed UK airspace for 3 days, causing complete havoc. Well, the eruptions 55 million years ago were quite similar to this, but they were much, much larger. So it's lucky we weren't trying to fly aeroplanes. So I'm studying these ashes for my PhD. But the important question is, what makes volcanoes go bang? And why were these eruptions so large? So normally you have the explosivity of an eruption is kind of affected by the chemistry of a magma and the stickiness of the magma and how many gases it contains. So I'm guessing by now, hopefully, you've all had a couple of drinks, you know, there's a break coming up, you can get another one in a minute. But maybe you're beginning to feel the effects of those drinks. You can start to feel the gases building up inside your stomach. So at home, then, you might, you know, pass wind here and there, and you'll be fine by bedtime. But right here, right now, maybe that's not socially acceptable. So you hold on to those gases and you feel them build up and up and up until you feel like you're going to explode. This is quite the same for the volcanoes. So if you have a sticky magma, one that contains a lot of silica, which is effectively glass or quartz, this binds the magma together and means that the gases within it can't escape. So the pressure builds up until the system can't take any more and you get an eruption. So as I'm sure you all know, the longer you hold on to those gases, the bigger the eruption is going to be. So this is quite similar actually to an iron brew. So if we have our iron brew here, our iron brew is the magma in a lovely magma chamber, and we have a little volcano at the top. So if I shake this up, pretend there's an earthquake at the volcano, and then could you open this? No, I'm glad you said that. So if you were, though, to open this lid, then you would have released the pressure that's built up inside the magma. The gases would expand, fragment the magma into variously sized volcanic rocks, which gets forced out of the volcano in a big eruption. So that explains normal volcanic eruptions, say normal. But the eruptions at this unnameable Icelandic volcano and the eruptions 55 million years ago weren't like this. For starters, they involved a magma that contained very little silica, which means that it was very runny, fluid, and not very sticky. So gases could easily escape. So you don't get the build-up of pressure, and you can't form a big eruption. But big eruptions did occur, so why is this? How did they occur? Perhaps it's because the magma came into contact with water. So, we have when water and magma interact, the water is rapidly flashed to steam. So it's quite like if you imagine water fizzing about a heated frying pan. The water rapidly flashes to steam while we still have our gases expanding in our erupting magma. So this fragments that magma further, forming much, much finer material, so volcanic ash. So from this we get lots more volcanic ash, and ash is very buoyant, so it gets lofted to greater heights in the atmosphere, where it can be transported to much greater distances away from the volcano. And these eruptions involving magma and water are known as hydrovolcanic eruptions, so water and volcano, but they used to also be called phreatomagmatic eruptions, which sounds much more dramatic. So these eruptions are well known throughout history and are probably responsible for some of the largest and most deadly eruptions that we know of. So, for example, the spectacular end to the AD 79 eruption of Vesuvius, which killed the inhabitants of Pompeii and preserved them. That was caused by magma coming into contact with groundwater beneath the volcano. And again, at Krakatoa in Indonesia in 1883, seawater came into contact with the magma chamber, which formed a huge blast, which produced the loudest sound in recorded history. So this was heard as far away as Australia, and it was heard as cannon fire, and it was recorded all around the entire globe as a sudden decrease in pressure. So these interactions between magma and water can happen at any time, which makes them incredibly unpredictable. Now, we find it difficult to predict normal volcanic eruptions as it is. So, for example, you might maybe get some earthquakes, or there might be some small steam eruptions, or a change in gas composition at a volcano, or ground deformation, which might herald an impending eruption. Or, after all that, the volcano might go quiet. It might go back to sleep. And then all of a sudden, after that, it might just go bang and erupt and take everyone by surprise. So, what I was going to do is do a demonstration, have someone come up, have a load of iron brew bottles, some of which would have been nicely shaken, and have someone predict which ones were going to erupt. But I got told that we're not actually allowed to do that. And someone might get upset if they get covered in iron brew. So instead I go back to what I said earlier. So I had this iron brew, and I shook it up, there's an earthquake, and I was going to ask you to open it, and you said no. I reckon everyone in this room would have probably said no. Or I'd hope so. But the thing is, so you made a prediction. You predicted that this was going to erupt. And you made that prediction based on some assumptions. Maybe you assumed that I'd bought this iron brew this morning, had shaken it for the first time while I stand here, and was going to get you to open the lid for the first time, which of course would lead to an eruption. You were wrong. What you didn't know is that I've been carrying around this iron brew for a week. It's been sat on my desk, and I've opened it several times. I haven't drunk the stuff. But, so if you had opened the lid, actually nothing would have happened. So really this sums up my talk. Volcanoes are highly unpredictable. You can only base a prediction on things that you know or some small assumptions, but you don't know the whole story. And if this really was molten rock and we added water into the mix, then this would have become a lot more unpredictable and a lot more explosive as well. So these eruptions are hydrovolcanic eruptions, and they've occurred for some of the deadliest eruptions in history, so Vesuvius and Krakatoa. And they've plagued us here in the UK as well, right back from 55 million years ago to the present day, and they will affect us here again in the future. Thank you.